Hello, everyone. I know I have the challenging task of preserving everyone's attention as you all are thinking about what's for lunch. So I'm going to do my best to keep this nice and entertaining and also cute by using lots of puppy pictures. So today's agenda is pretty simple. Today I'm going to share with you how you can use serverless for on-demand compute, how the edge cases work, because I'm a site reliability engineer. I like to think not just about how things go right, but how things go wrong. I'll share a little bit of how to safely experiment with serverless in your environment. And then finally, I'll talk about environmental sustainability, since that came up at the start of the day as well. So first of all, let's talk about what you might want to use Lambda for. So I work at a company that produces a software as a service product. So let's talk about what the use case is that we concretely have. So we want to optimize our custom data store, and that's called Retriever, and hence the dog photos are going to enter very soon. But we can talk about, oh, there's this technology called Retriever. It's a distributed column store for real-time event aggregation, right? Like that might not mean very much. So we really should think about how do we make this concrete and relate to what users actually are trying to do with the software, right? So real-time event aggregation. We're talking about trying to analyze data that's coming from people's systems and trying to help them wrap their heads around what's going on. And the real-time piece is super, super key, because when you have a breakage in your system, you want to be able to get it working as quickly as possible. By the way, the dog is named Flurry. That is my and my wife's dog. So hello, everyone. I am a AWS community hero for the Graviton, AWS Graviton community, and I'm also the field CTO at Honeycomb, and I split my time between Sydney and Vancouver, which is a thing that you can talk to me afterwards later. So Honeycomb's goal is to make it possible for developers to reconcile their mental models of what's going on in their systems with what they think is going on in their systems. And the way that we do that is through enabling people to look at their structured logs and traces. So you heard a little bit earlier this morning about how you should have some form of monitoring and or observability. I do want to be clear that monitoring and observability are not entirely synonymous, because monitoring encapsulates looking at things that you anticipate in advance. So it might be, are my users seeing any errors? But monitoring will not necessarily tell you why your users are seeing errors, unless you happened to slap a monitor on the exact thing. But often, putting too many monitors in place doesn't really work that well. It's like you put a monitor on your AWS RDS database utilization, that's fine. But then if you put a monitor on the CPU utilization of every single pod, that's maybe going to alert and not necessarily give you signal. So in contrast, observability is much more about free-form exploration. What do you want to look at? Where is the trail of breadcrumbs leading you so that you can figure out what's going on? And rather than only selected pre-indexed things being fast, everything is fast. So this is where I normally would show a video, but instead of showing the video, I figured I would try my luck with a live demo. So let's have a look at how many AWS Lambda invokes happened in the past couple of minutes. So name is invoke, service.name is Lambda. And let's group this by tenant ID, just for the hell of it. So this will be environment ID. So I'm just going to set that running. And you can see that it comes back pretty quickly. And it says, you've got one customer that's running a lot of Lambdas that is invoking, looks like basically 500 invokes per second. That's pretty exciting, actually. Let's filter that customer out. And for the remaining customers, let's go ahead and filter this down and look not just at things that are running from cron, but let's look at things that only come from real users. So query app.query source is normal. So this is what I mean when I talk about being able to look at your system. So this is Honeycomb dog fooding Honeycomb, right? So this is looking at what our Lambda usage looks like in real time. And you can see basically, we've got this one customer that someone's currently doing a, little bit of investigation. Who's that, right? Like, so there's this one person here that ran a really large query but hasn't really done anything else for the past 2 hours. So that's the kind of thing that we mean when we talk about real-time exploration. And, the idea is that you should be able to not just aggregate by one dimension, but be able to aggregate or filter by multiple dimensions together. So the ingest piece is something where, you want to get a load of data out of people's systems into your own systems. The best way to do that is with a technology called OpenTelemetry, which is open source, and I think New Relic is in the sponsor hall, so we and New Relic and a number of other companies collaborate on this open standard for how you produce this data so that you're not locked into any particular vendor, right? Or you could even use something open source. But the magic that I wanted to share with you today is how all of this winds up, how we make it fast in our specific case. And our implementation is fast because we focus on trying to minimize the amount of data that you have to query and being able to brute force it as quickly as possible. Oh, and by the way, now with AI, so for instance, why don't I just start this query over again and, oh, well, that was a spectacular live demo fail. Let's refresh that. Okay, there we go, better. Okay, so what if we said, how many spans with the name invoke were made grouped by architecture? So, just because I can, there we go. So 4 million something invokes on the ARM architecture and 45,000 invokes on the AMD 64 architecture. Yes, thank you, Honeycomb Query Assistant. That did work. But we have to sprinkle a little bit of AI, but only where it makes sense, right? So, importantly, not just for the sake of live demoing, but also because I think it's important to when you're actually having an incident. 100 milliseconds, great. 1,000 milliseconds, you can start seeing the spinner. That's probably fine. But if it takes 10 seconds, you're like, what's going on? Is everything okay? And if it's taking 100 seconds, that's okay, my users are broken. What's going on? I can't fix it. So speed is everything when it comes to being able to debug. So we wind up having all of our architecture really optimized around speed to ingest data, speed to get it offloaded onto AWS S3 as quickly as possible, and then we are able to query it. So originally, it didn't used to be this way. Originally, it used to be you would have your OpenTelemetry data stream, and it would get streamed through Kafka, and it would sit on a local solid-state drive. And originally, prior to Honeycomb existing, it was derived off of a Facebook product that was internal to Facebook called Scuba. And Scuba stored all the data in memory. Guess what? None of us are well, maybe there's some people here who work at Meta, I don't know. But most of us cannot afford to keep all of our telemetry data in memory. So we kind of have to figure out a way to store it more economically. So, okay. Local solid-state drive, you go and, essentially run the moral equivalent of grep over data on local NVMe storage. So that works until you fill up your NVMe drive, and then that's not so great. So maybe you expand horizontally, so you say, okay, I'm going to go ahead and run this query across multiple parallel hosts, so maybe each event that comes in gets written to an arbitrary host, and we can query all of those hosts in parallel, and then they'll all come back and everything's fine. And when we're talking about sifting through the data, you don't want to have to sift every single field if you're only interested in, maybe 3 fields or 4 fields. So if you break it out by field, it has the advantage of you can both have it compact down super finely because a lot of the values in each field are repeated. And also, it makes it so that the data is segregated, so you only have to query the data that's specific to your use case. All right. The other piece is only querying what you absolutely have to, right? If I ask a query about, what happened in the past 2 hours, I don't need to scan the data from 30 days ago, right? I don't need to scan the data from 4 hours ago. I just need to scan any possible data that could have come in between 0 seconds ago and 7,200 seconds ago. So when you have things organized both by field and by timestamp that the data comes in, that kind of gives you some traction as far as being able to relatively efficiently analyze it locally. So we have a query time range, and then we are searching the overlap. So that's how we kind of get that magic to happen at smaller scales, but we encountered a problem. The problem was data volume increases year on year, and the size of your local SSDs does not. And sure, you can add more and more and more horizontal processing workers, but at a certain point, it gets too expensive. So at a certain point, you start to have to say, okay, we're going to throw out the least recent data. Because, probably you're most interested in something that in what just happened. Maybe data from 7 days ago. If push comes to shove, you're going to throw out the data from 7 days ago to have access to what happened minutes ago. But really what wound up being better and more efficient is just, the data from longer ago is still valuable. It's just not accessed as often, and maybe people are okay with a slightly longer wait. So it doesn't have to sit in hot storage. Let's tier it off to AWS S3. But the thing that we are still doing was if we had to query that older data, we are sucking it back down onto those local, very serverful machines to try to get it to give us results. So now you can keep data all the way up to 60 days. You don't have to worry about expiring it out early, and everything is gravy, right? Well, there's a problem, and the problem looks like this. The more data you're scanning, if you're scanning it on a finite number of CPU cores, then you are taking longer and longer, and that means that people are not having a top-tier experience. So essentially, this is the problem that happens, is that people click that run query button on a very unpredictable schedule. It's like, does my dog want to play with her toys or not, right? And when my dog doesn't want to play with her toys, I don't want to leave them strewn all over the floor, right? I don't want to have, hundreds of VMs just sitting around unutilized. So fortunately, we are at Serverless Days, so let's talk about serverless. So the wonderful technology of your favorite cloud provider, in my case, AWS. So we have AWS Lambda. And AWS Lambda enables us to get tens of thousands of workers with, somewhere between 4 and 8 cores each, just on demand, on the fly, whenever we need it. And we don't have to pay a cent when we're not using it, which is pretty cool. So because we already offloaded the data to S3, it means that it's possible for Lambda to reach out to S3 and query that data rather than have it all be bottlenecked on the central host. But you do need to kind of have one place to aggregate the data and merge it back together. So now the local node is definitely still processing data from maybe the past minute or two, but now everything else is flowing out to Lambda to query the data on S3. And now you have a much more delightful experience where even if you're querying 60 days of data, it might only take 10 seconds or, heaven forbid, 30 seconds if you're running a super complex query. So the cool thing is, when I say it's really, really on demand, I mean it. AWS, in the past 3 years, I think, reduced the minimum buy of when you run an invoke. It no longer bills you for a minimum of 100 milliseconds. It actually bills you for a minimum of 1 millisecond. That means if you make your function 1 millisecond faster, you're paying less money, which I think is really cool. So this is theoretically how this works, right? You have, even in the case of a cold start, it's taking something like 50 milliseconds to spin up. A majority of our queries are able to respond within 2.5 seconds, and it's only 3 to 4 times as expensive as EC2, which you may look at that and go, oh my God, why would you pay 3 to 4 times as much? And then you remember, we get 100% utilization this way. If we had to keep these, 10,000, 20,000 workers running flat out, and then there were a window of time in which no one ran a query, let's maybe look at 24 hours ago, and let's, conference Wi-Fi, please cooperate with me. There we go. So if we look at 24 hours of data, and we look at this lull right here, so if I zoom in on this lull right here, you can see we had not a single soul run a query in this window between, in this window between, let's change this to UTC just to make the pedants happy with me. Okay, so in the window between 5:21 UTC and 5:22 UTC, basically no one ran queries during this window, right? Why should we have to pay for compute that's not useful? So this actually winds up being a pretty good bargain, right? And the other cool thing is that we don't have to manually capacity plan anymore. We can just grow and grow and grow and grow, and it all works out fine. So Honeycomb is petabyte scale now, and everything is glorious and sunshine and rainbows and unicorns, right? Now we get to part 2 of the talk. Lambda is on-demand compute, but they didn't originally build it for this, so let's talk first about the scaling dimension. Yes, you can scale, and in theory, Amazon handles all of your capacity planning for you, but how many of you have ever encountered a 429 error? Okay, right, like that happens when you try to do too much at once and Amazon doesn't have enough of your particular runtime that's pre-warmed up and ready to go, so they have to go ahead and spin that up somewhere. So it's not just a matter of paying the cold start tax, it's also a matter of having that available and ready to run and having the capacity ready. So it used to be that you had to sustain your load for 1 minute and then you would get an increment to your burst limit, but the good news is now it's 10 seconds, which is awesome. So you can scale up by 1,000 concurrency per 10 seconds, which really, really makes the economics of this work a lot better. We still manually capacity plan with the AWS service team though. So we actually measure our concurrency and make sure that we are getting what we negotiated with our service team, and if there's a problem, then we can communicate about it, which I think is pretty cool. So make sure that you retry 429s, right? Like make sure eventually the capacity will be there and you can actually invoke, and talk to your account reps. So the next thing, median startup time. It turns out averages, percentiles, they all lie. Latency is a shape, so functions start up when they do. So in this case, this is a cold start that took 13 milliseconds, but some cold starts can be considerably longer. And if you add instrumentation to your Lambda main function, you can actually track how many of these Amazon is running for you and that just are sleeping and not currently doing anything, but are ready to wake up in a moment, and versus how many of them are actually currently in use. The other thing is when you're working with systems like Lambda and S3, they are large distributed systems, they're operated by not you, and there will be tail latency cases. So 90% return within 2.5 seconds, but some never return even after 30 seconds, and some of that may be because the worker never got the call, others may be because the S3 request never completed. So the good news is, in our case, item potency, reading is an item-potent operation. So we just retry it, and in fact, we just retry the slowest 1% of requests. If 99% of all the other lambdas for a given query execution in Honeycomb have come back, then we just retry the last 1%, and failures are usually not sticky. So if you retry an S3 request that failed the last time, it'll succeed the next time. Other weird bits. So, you heard earlier about use of DynovoDB and reading things and putting things on and off of a pipe. If you're trying to poke things with an explicit invoke request rather than have it be driven by a pipeline, it only accepts JSON. That's expecting that you are sending data from an API gateway. But we're not sending API gateway type requests. We're sending the specification of the query, right? We're sending, let's look at the query definition, right? We're sending something that looks vaguely like this, right? What's the calculation? What are all the operations you're asking me to do? And we're sending it a list of files, but we have to serialize that from protobuf to JSON, and then on the other side, we have to decode the JSON. It's a little bit silly. AWS reps, if you're listening, please fix this. Also return values. Some of our results are really, really big, so 6 megabytes is the maximum, so past that you have to throw the result in S3 and return a link to it instead. And finally, I talked about the expense, right? So it's great, you can scale up indefinitely, you don't have to pay for utilization that you're not using, but unlike running a fixed number of servers, there is no cap on how much money you can spend with Lambda. This is not good. How many of you have ever circularly invoked lambdas and accidentally created? Yeah, I see the folks in the back know this, right? So you can easily run up a bill of $10,000 in the matter of a day, or even $10,000 in a matter of an hour. Usually Amazon is pretty good about forgiving it if it's a mistake, but in our case, we want to make sure that our customers are costing us a reasonable amount of money. So if you are a Honeycomb customer in the audience, this is why we put limits on the query data API, so that you can't, query 7 days of data every single minute, over and over and over again. But we keep metrics on that, and we set alerts on how expensive it is, because it turns out Lambdas billed by the second, so there's a by the milliseconds, there's a very nice conversion from milliseconds of runtime to what the cost is. So if I show you the Lambda cost, so we literally have a function here that is computing the amount of function memory assigned and the architecture, and then assigning a value per millisecond of compute. So what if we could make it less? What if we could make this sustainable both for the Earth and for our business? Well, so in 2021, AWS released Graviton 2-powered Lambda functions, and I'd previously advocated for ARM, right? Like, I was like, hey, like, let's try this on our server full stuff, and it worked in, let's say, 40%, pretty cool. So I was like, wouldn't it be great if I could just push one button, because we're already building for both architectures? What if I could just push a button, change a config, and make everything 40% cheaper? Wouldn't that be nice? So I pressed the button, and our cost went up. That was not so good. It turns out that you have situations where not every workload is perfectly optimized for every architecture. So in particular, what happened was we did a 50% A/B test, and of the 50% that were running on ARM, they ran twice as slow. So that was not great. So we wound up having to revert it and then do some performance tuning, and basically there wasn't enough capacity. Like, you turn on a brand new AWS service that's just been released, and you set it full throttle, and of course it's going to queue because they haven't provisioned capacity yet. More mature AWS services tend to have more capacity behind them. But also there are a couple of underlying things that we fixed, and then send layer performance was much better, and we were able to shift over to 99% ARM and save a truckload of money. And you can see why this was important to the sustainability of our business, because you can see that cost curve of x86 going up and up and up to the right. Not all graphs that are up and to the right are good. And we reset that curve, and now it's more sensible with our economics. So this is what that looks like roughly today. So yes, experiment with serverlessing your database and your big data applications at home. The key here is you have to have a data pipeline, right? Like DynamoDB or like S3, so that all of your Lambdas have access to all of the storage that you're operating on. And essentially, it becomes a glorified MapReduce of sharding and parallelizing and reducing. Just don't necessarily do it for things where your workload is predictable. If your workload is predictable, cost-wise, you're much better served just using a longer-lived VM. Tiny workloads also, like, maybe don't incur that startup latency. And talk to your cloud provider about anything you're doing if you're doing largely at scale. Let's see. So nothing matters unless developers are happy. So in this case, I prefer to to make sure that my dog is happy. So if you're interested in learning more about our storage engine, I'll leave this slide up on the screen for a second. There is a free copy of our observability engineering book. This is chapter 16, where I talk about this. I wrote that chapter. And this is Flurry. Flurry is a lovely golden retriever who I love very much, and I thought I would end my talk on that. Thank you very much.
Thank you, Liz. All right. Are you up for a question or two? If there are some, we have time for a couple of questions if you're up for it. Otherwise, it's fine.
Yeah, absolutely.
Yeah, does anyone want to ask Liz a question about this? Who here uses serverless VMs? That was a trick question.
The funny thing, though, right, like, is that it's I know we said, don't say, oh, servers are actually, serverless is actually servers, but like in our case, this is actually relevant to talk, right? Like, serverless is actually servers. Amazon has to rack and provision your machines, so.
Very much, very much. Right, I think people are hungry. What do you reckon? It looks like it, doesn't it? There is food in there, and it is delicious. So, and then there's a question. Really? Okay, fair enough. Just as I said that.
For the capacity bursts, do you jump into a different region, or is from scalability just for the availability?
If we had to, so far all of our capacity bursts are mostly addressed by having enough capacity allocated to us by Amazon such that we can burst into it. If we had to, we could reduce from 99% ARM to 75% ARM. Right, so that's actually why we still have that 1% holdback of 1% x86. We want to make sure that we do not break anything for x86. just the opposite situation most people have. Most people are like, I'm just trying this ARM thing. I don't, I'm test running it. So actually, we're now test running x86 to make sure we didn't break compatibility, so that if we needed to, we could change the feature flag and then get more capacity essentially instantly available, because there's a huge pool of x86 Lambda capacity compared to ARM. Also, yeah, I think theoretically we could go into US East 2 from US East 1, but like that incurs data transfer charges, and that would make, we would not want to do that unless we absolutely had to, because that would cost a lot more money.